This video shows a simulation of NRZ and RZ signals. These are basically line codes. They transform the digital inputs, that's 0 and 1, into suitable formats so that they can be transmitted over a physical channel. That is conversion of the digital bits into suitable voltage levels. So now let us see the simulation of an NRZ signal. So we will need a binary input source. So there's one binary input generator in Simulink, that is the Bernoulli's binary generator. So type in Bernoulli in the library browser and click enter. So you have this block. You can either drag and drop it on the screen or right click on it and give add block to model. So the block will be added over here. Place it wherever you want. Next, what logic we are using here to generate the NRZ signal is, we will consider a switch which varies between two voltage levels. The switch has a threshold now. So it decides whether the input which is arriving is 0 or 1 and selects the voltage level based on the input. So we will need a switch. Go to the library browser, type in switch and give enter. So you have the switch and drag and drop it and I'll place it over here. Next, we will convert this into a bipolar NRZ which gives a +1 voltage level and -1 voltage level, which maps to 1 and 0 respectively from the input. That is, if the input is 1, the voltage level will be +1. If the input is 0, the voltage level will be -1. So to generate these voltage levels, these are constant voltage levels. So we'll take a block called as constant. So there's a constant block over here, drag and drop it. This constant says +1. We'll take another constant -1. You can just replicate this block by holding onto the right mouse button and dragging it. So you have another constant. So here the constant value has to be changed. It has to be -1. Just double click on the block. It will open the properties window. Here the constant value can be given as -1 and just hit enter or give OK. So you can see that the value is changed to -1 here. Now we will generate an eye diagram also to just visualize how the noise, when the noise is added, how the output will look. So we'll need an eye diagram block. It is inbuilt in Simulink and you need not do any different mathematics for generating an eye diagram. So just give eye diagram, hit enter. You have this block over here from the communication system toolbox. You can either directly search items from here and you will get it here, or you have various system toolboxes here. You can go to each and you can explore what all are there. So let's just drag and drop the eye diagram block. So now to generate the eye diagram, we will need some noise to be added to our signal. So we will add the noise. How to add noise? Just go to the library browser and type in noise. You have a band limited white noise block over here. It's a simple type of noise. We will take this and we will place it over here. Now, next thing is to add these two signals. That is our NRZ signal and our noise signal and give it to the output block, eye diagram block. So we have to add, we need an add block. You can give either add, sum or anything. You will get all the blocks associated with it. So here you can see there are various blocks. Let's give take this simple addition block and place it over here. Now to visualize our outputs, all the signals that we are getting, we will take a scope, the oscilloscope. The keyword is what is used in Simulink is called a scope. So take a scope, drag and drop it. So now here you can see you can only attach one signal to this scope. So we need more signals. We'll need 3 signals in this case. So double click on the scope and go to this configuration properties. It will open. So there's a part which asks you to input the number of ports. So we'll give 3 over here and give enter. You can take any number of input ports that as you need. So let's just close this for time being. Now you just expand the scope so that you can distinguish the signals that are available here. Now we'll make the connections. So the input is given to the switch, the center port of the switch. Then the top part is given to the constant +1. The below one is given to the constant -1. Then the signal, our NRZ signal which is coming, is added with band limited white noise, so it's given to two input ports of AND. Then this is given to our I diagram. Now, what all we'll see in the scope? Now, first we'll see our input signal, whatever we are getting from the Bernoulli generator. Second, we will see what NRZ signal that we have generated. And third, we will see what has happened to the signal after addition of noise. The connections are done now. Now we have to see what are the properties. We have to set the properties so that the system works as we need. Now let's go to the Bernoulli's binary generator. Here you can see that the probability of 0 is 0.5. You can set it to any value between 0 and 1. It will influence the number of zeros or ones that your input system will generate. Now let's say I'll make it 0.4. You can set it any value, this doesn't matter. Sample time is 1, samples per frame is 1. This is all fine. Keep it as default, give OK. Now let's go to the switch. So here there's an option to give threshold. The threshold is by default set to 0. But what threshold we need in this particular experiment? So our input varies between 0 and 1. So to decide whether the input is 0 or 1, we will have to consider the midpoint of 0 and 1. So that is nothing but 0.5. That will become our threshold. So set the threshold as 0.5 and give enter. You can see that even the value will be changed inside the block. Now we will add the noise. So go to the noise. The noise cover is given to be 0.1. This is quite high and the eye diagram will not be visible properly. So we'll make it a lesser value so that we get a cleaner picture. So say 0.0001, I set it. You can set different noise powers and see how the system works. It's fine. So now let's just give OK. Now let's go to the eye diagram block and also set its properties. So go to the configuration properties over here. You can see that the samples per symbol is 8, but our samples per symbol in the input was 1. So make it 1. So symbols per trace, this is around 50. This is just to visualize many number of lines so that the output can be viewed nicely, neatly. So then traces to display is also 20. You will get different lines over here. Then OK, just give OK. You can see that this value has gone till 50. So now let's just close this. Let's open this after the simulation has been done. Here you see that there's an option to give the simulation stop time. This value will be generally 10. You have to set the value to 100 for this particular experiment so that you will get many data points. So now I have set this to 100. Now just click run and let's see what outputs we are getting. So automatically the eye diagram opens. See, if you don't want that to happen, you just can go to file and uncheck this option, the open start simulation. So now this is the eye diagram. I'll just maximize it. So this is how the eye diagram has to be. I'm not going into the details of why the shape is like this. It's a theoretical aspect. But if you're getting the eye diagram like this, then it is correct. Then we'll visualize how the scope outputs are. Double click on the scope to visualize the outputs. I'll just maximize it. Here you can see all the waves are overlapping. To differentiate them, just go to view, click on layout, and hover over the layout board to see in what way you need the signals. So when you come like this, you have an option to display 3 signals, one below the other. So once you are fixed with the layout that you want, just give a click and the waves will be separated. So here you can see that the first port what we had given was our input wave. Here you can see the input is varying between 0 and 1. That is our digital input, 0, 1, and so on. So what we had done, we had generated our NRZ wave, which varies between 1 and -1. So here you can clearly see for an input value of 1, our output NRZ signal is +1, and for input value of 0, the NRZ signal is -1. So our NRZ signal has been effectively and correctly generated. And the third one, whatever you see here, is the NRZ signal with the noise added. Here you can see that there are variations in the end limits. These are the noise factors that we gave through the band limited white noise. So you can just give the names to these signals by going to configuration properties, then go to display, then active display says 1. So the title of the first wave, we'll just give it as input wave and give apply. So here you can see that the first wave was named as input wave. Now just make the active display as 2 and change this name as NRZ Signal and give apply. Then you can see here that the name has been changed to NRZ Signal Similarly, third one, I'll just name it as NRZ with noise, and I'll give OK since all the naming has been done. So here you can see that it's named as NRZ with noise. Similarly, you can change the background color, you can disable these grids that have come, and you can do all the formatting that you require to give a better visualization to the observer. So this is how you generate the NRZ signal. This is done, this is fine. Now, with the small variations to the same circuit, you can make the RZ signal. Now, what is the difference between NRZ and RZ? In NRZ signal, you observe that the signal was never coming back to zeros. So in RZ signal, what we have to do is we have to make the signal come back to zero. That is, each sample has to return to zero. For example, let us say here for each second there was one sample that was spanning the entire second. Here we'll make it for 0.5 seconds. It will be at 1. Then it for 0.5 seconds it will be at 0. Then another 0.5 seconds, for example, for a 0, it will be at -1. Another 0.5 seconds, it will return back to 0. So this is how the RZ signal is generated. So all the input components, the switch, everything that you need is the same. What we need to do is multiply this NRZ signal with a pulse which is half the symbol duration. So we will not consider eye diagram for this. This is fine. The eye diagram is working. So we'll just delete all these blocks that we don't need. We'll delete the add block, and we'll delete all the unnecessary wires over here. And we'll also take out the noise. So this basic circuit remains the same. Now you will have to take a pulse generator to generate pulses of half the time period to generate an RZ signal. So just given pulse, you have a pulse generator. Click and drag it and place it over here. Now what I said is we need to multiply these two signals. So we'll take a product block. You can even give multiply. It will give the same set of blocks available. So here there's a simple product block. Take it, place it over here. Now one input is the pulse generator. One more is our NRZ signal. So we need to now set the properties of the pulse generator. Double click on the pulse generator. Here you can see the amplitude is 1, which is fine. Now the period, make it as 1 second. Then give OK. Now let's make the simulation time as 10 so that we'll get a lesser number of pulses and we can actually see how it is returning to 0. Now give run. Double click on the scope to view the output. Here, this is our input wave. This is our NRZ signal. This name we will change it. This was from the previous one. Go to display. The third one. This is nothing but our RZ signal now. So this is changed to RZ signal. Now you can see what is happening. When the input is 0, the signal is at -1. This is at NRZ. Now that is converting into RZ. What is happening is for half the time period it is -1, then it is returning to 0. Again for half the time period it is -1 and it is returning to 0. Similarly, for an input of 1, you can see that for half the time period it is +1 and it is returning to 0. So this is the functionality of the RZ signal. So this is how you can generate both NRZ and RZ signals using Simulink. Thank you.